Hi guys! Welcome to Science Moment, a place to ask the big questions, to seek the hidden truths, and to marvel at the sheer scale of the universe we call home. From the dawn of time, humanity has been obsessed with speed. We want to go faster, fly higher, and surpass our own limits. And then, as science advanced, a seemingly simple question began to emerge. Does a maximum speed exist in the universe? Today, we know that light travels at a speed of nearly 300,000 kilometers per second, so fast that in the blink of an eye, it could circle the Earth more than 7 times. But the strange thing is, nothing can surpass it. No spacecraft, no particles, no information can travel faster than light in a vacuum. Why is this the case? Is this merely a temporary technological limitation? Or is it a profound law, woven into the very structure of space and time? If you could surpass the speed of light, what would happen to time, to cause and effect, to the past and the future? In this article, we'll journey from the oldest conceptions of light, through physics-shaking experiments, to Einstein's theory of relativity, to understand why the speed of light is not just the fastest speed, but the foundation of reality. Chapter 1: The limits of the universe's speed. Why does an absolute speed exist? For much of human history, light seemed to have no speed. When you lit a fire, the flame flared up instantly. When the sun rose, light filled the sky without any perceptible delay. Given this experience, it was perfectly natural for humans to believe that light travels instantaneously. The philosopher Aristotle, who has had the most profound influence on Western scientific thought for nearly 2,000 years, asserted that light does not move. It is everywhere at once. There is no reason to doubt this, as no experiment sophisticated enough to prove otherwise. But the universe doesn't operate according to human intuition. Today, we know that light has a definite speed, about 300,000 kilometers per second in a vacuum. That number isn't just large, it's fundamental. It's not the greatest speed humankind has ever measured, but the greatest speed anything in the universe can reach. The question immediately arises: why is there a speed limit? Why doesn't the universe allow everything to accelerate infinitely? In everyday life, every speed limit has a clear reason. Cars are limited by their engines, friction, and material strength. Airplanes are limited by air resistance. Rockets are limited by fuel and technology. But the speed of light is different. It doesn't depend on technology, it doesn't depend on materials, and it cannot be surpassed, even in principle. This makes the speed of light limit seem strange. It's not a technical barrier. It's a rule of reality. If you try to imagine exceeding the speed of light, the consequences immediately become alarming. Suppose you could send a signal faster than light. In some frames of reference, that signal would arrive before it was sent. In other words, the effect would precede the cause. The causal order, the foundation of logic, science, and human experience, would collapse. Not only is time disrupted, space is also becoming unstable. Distance, clocks, the sequence of events, all lose their objectivity. The universe will no longer be a sequential story, but a chaotic mess where everything has happened and yet to happen. The amazing thing is, the universe doesn't allow it. No space police are needed. No laws are necessary. The very structure of space-time prevents exceeding the speed of light. The speed of light is not just the speed of photons. It is the speed at which information, influence, and cause and effect relationships can propagate. Anything that can carry information, from electromagnetic waves and fundamental particles to gravity, is limited by this speed. This leads to a completely new perspective. Light not only helps us see the universe, it shapes how the universe works. Ironically, this limitation, instead of being restrictive, creates order. Thanks to maximum speed, events are arranged in sequence. Thanks to it, cause always precedes effect. Thanks to it, the past is not influenced by the future, and reality becomes stable. Humans once thought that light was immeasurable, but when we began to measure it, we realized a much deeper truth. Light is measuring the universe itself for us, measuring the boundaries of what is possible. To understand why this limitation exists, we must go back to the moment when humans first suspected that light was not instantaneous. A seemingly small discovery, but enough to shake the foundations of classical physics. In the next chapter, we will follow the first scientists who measured the time of light, and inadvertently unleashed the greatest crisis in the history of physics. Chapter 2: How do humans measure the speed of light? For millennia, the question "how fast does light travel?" was not posed out of curiosity, but because humans lacked a way to answer it. On Earth, distances are too small. Light travels across them faster than any ancient clock could record. Therefore, intuition triumphed over science. Light appears to appear instantaneously, even if there are skeptical voices, such as the philosopher Empedocles' argument that light needs time to travel. They are not convincing enough. There is no evidence, no measurement, and no practical reason to argue with Aristotle. Everything only changed when humans began to look beyond Earth. In 1676, the Danish astronomer Ole Rømer studied the motion of Io, a moon of Jupiter. Io orbits Jupiter with a very regular cycle, constantly disappearing behind the planet and reappearing. This made it an ideal cosmic clock. But Rømer noticed something strange. The timing of Io's appearance didn't always match predictions. When Earth approached Jupiter, the phenomenon occurred earlier. When Earth moved away, it was delayed. Initially, this discrepancy might be considered an error. But it's not random. It repeats in the cycle of Earth's orbit. Rømer came to a bold conclusion: light takes time to travel. When Earth is farther away, light from Io has to travel a longer distance, so it arrives later. For the first time in history, the speed of light is no longer a philosophical assumption, but has become a measurable quantity. Although Rømer's measurements were not precise, his ideas opened the door to modern physics. Light is not instantaneous. It follows laws. 2 centuries later, humans had the technology to measure the speed of light right here on Earth. Hippolyte Fizeau used rotating gears and reflecting mirrors to calculate the time it took for light to travel to and from its destination. Léon Foucault improved this method with rotating mirrors, achieving greater accuracy. Each experiment led to the same conclusion: the speed of light is finite, fixed, and measurable. But the most important discovery wasn't the number itself. It was what happened after that number was measured under different conditions. In 1887, Michelson and Morley conducted an experiment to detect the Earth's motion through a hypothetical medium called the ether, which was thought to be necessary for light to travel. If the Earth were moving, the speed of light would have to change in different directions. Result: nothing changed. Even though the Earth is moving and the direction of measurement changes, the speed of light remains constant. This directly contradicts classical physics. There is no way to explain this phenomenon without breaking familiar concepts of space and time. The Michelson-Morley experiment not only failed to find the ether, it succeeded in creating a crisis. A crisis that forced physics to fundamentally change. And it was from this impasse that a completely new way of looking at the universe emerged, paving the way for Einstein and the theory of relativity. Chapter 3: The Crisis of Classical Physics. When intuition is no longer accurate in the world of classical physics, everything operates according to seemingly logical rules. Space is a fixed stage. Time flows equally for everyone. And velocities can be simply added together. If you are on a moving train, your speed relative to the ground equals the train's speed plus your foot speed. This principle, proposed by Galileo and used by Newton throughout classical mechanics, works perfectly in everyday life. It explains the motion of a bullet, the orbit of a planet, and almost every phenomenon that humans can observe with the naked eye. But light doesn't follow that rule. According to classical mechanics, if you run in the direction of a ray of light, you should measure it to be slower. If you run in the opposite direction, you should measure it to be faster. This is a natural consequence of velocity addition. But every experiment, without exception, has shown the opposite result. The speed of light is always the same. This puts physics in a dilemma. Either light doesn't follow the general laws of motion, or the fundamental concepts of space and time are wrong. Initially, scientists chose the less painful approach, trying to maintain absolute space and time, then adjusting other details. The concept of luminescent ether was introduced as a medium for light transmission. It was assumed that the Earth moved within the ether, and that measuring instruments were affected by that movement. But the Michelson-Morley experiment completely shattered this hope. There was no ether. There was no light wind. There was no change in velocity in the direction of Earth's movement. Classical physics now faces a serious contradiction. Maxwell's equations describe electromagnetic waves for a fixed speed of light. Newtonian mechanics requires that velocity must depend on the frame of reference. Both are true within their respective scopes, but cannot be true simultaneously. This is no longer a matter of a faulty measurement. It's a matter of theoretical structure. If light always travels at the same speed, then time cannot be absolute. Because if time flows the same for everyone, there's no way the velocity would remain constant in every frame of reference. Some physicists, such as Lorentz and Fitzgerald, proposed that objects contract in the direction of motion when passing through ether. This hypothesis explains experimental results, but it is a patchwork. It doesn't explain why the contraction occurs. It simply assumes that it exists. Physics at this point is like a makeshift machine. It still works, but it's no longer consistent. Each new phenomenon requires a new assumption, and each new assumption makes the theory more fragile. This crisis reveals a crucial truth. The intuition formed from the slow-paced world of humankind is insufficient to comprehend the universe at the speed of light. To move forward, physics needs a more radical perspective, one willing to sacrifice the most obvious, absolute space and absolute time. Only then could the paradox be resolved. And it was at this point that a young official at the patent office in Switzerland entered the history of science. Chapter 4: Einstein and the Special Theory of Relativity. When space and time change in 1905, physics was in a state of uncertainty. The most accurate experiments showed that the speed of light was constant, but no theory could explain it without contradicting itself. It was in this context that Albert Einstein, then a young employee at the Bern Patent Office, offered a completely different perspective. Einstein did not attempt to correct classical mechanics. He accepted experimental results as a fundamental truth, then asked a bold question. If the speed of light is indeed the same for all observers, what must change? His answer was not light, but space and time. Einstein based his theory of special relativity on two simple but revolutionary axioms. First, the laws of physics are the same in all inertial reference frames. No frame is special over another. Second, the speed of light in a vacuum is an absolute constant, independent of the motion of the source or the observer. These two propositions seem harmless, but when placed side by side, they force the universe to pay a very high price. If light always traveled at the same speed, then time could not flow the same way for everyone, nor could space maintain its length under all circumstances. In other words, time and space are no longer absolute. Before Einstein, it was believed that two events happening simultaneously to you were also happening simultaneously to everyone else. The theory of relativity showed that this was not true. Two events could be simultaneous to one person, but occur before or after another, depending on their movement. Space and time, once considered two separate entities, now merge into a single structure, space-time. Every event in the universe has not only a location but also a moment in time. And how these events are arranged depends on the observer's state of motion. The important thing is, this is not an illusion. The clock actually runs slower when moving faster. The scale actually shortens in the direction of movement. These effects have been confirmed by numerous subsequent experiments. Einstein didn't say that everything is relative. On the contrary, he showed that there are things that are more absolute than ever, the laws of physics and the speed of light. It is precisely because these things are immutable that space and time must be flexible. Special relativity completely resolves the crisis of classical physics. It explains why the Michelson-Morley experiment yielded zero results. It harmonizes mechanics with electromagnetism. And, more importantly, it redraws how humans understand reality. From this point on, the question "why can't we exceed the speed of light?" is no longer a technical question. It becomes a question about the nature of the universe. If light is the maximum speed, What happens when an object approaches that limit? The answer doesn't lie in the engine or the fuel. It lies in the energy, the mass, and the deepest structure of space-time. And that's what we'll explore in the next chapter. Chapter 5: Why is it impossible to reach the speed of light? After the advent of special relativity, the question why can't we exceed the speed of light ceased to be a philosophical mystery. It became an inevitable consequence of mathematics and experimentation. No prohibitions were needed. No alternative hypotheses were necessary. The very structure of space-time rejected it. In classical mechanics, acceleration is a simple process. You apply force, velocity increases. The greater the force, the greater the increase in velocity. There are no natural limits. Given enough energy and time, you can, in principle, achieve any speed. The theory of relativity shatters this intuition. When an object begins to accelerate and reaches velocities significantly exceeding the speed of light, the relationship between energy and velocity is no longer linear. Initially, everything seems familiar, but the closer you get to the speed of light, the more you realize that each additional unit of velocity requires more energy than the previous unit. Not just a little more, but a lot more. According to the equations of relativity, as an object's velocity approaches the speed of light, the energy required to continue accelerating approaches infinity. This is not a technical limitation. It doesn't depend on the type of engine, fuel, or technology. Whether you use jet propulsion, antimatter, or any conceivable mechanism, the energy requirement remains constant. To reach the speed of light, you need infinite energy. And in a finite universe, that's impossible. This is the most fundamental reason why objects with mass cannot reach the speed of light. The concept often mentioned in this context is mass increases with velocity. In modern physics, this term is less commonly used, but it remains intuitively useful. When an object moves quickly, it resists further acceleration. It behaves as if it has more mass, making it increasingly difficult to speed it up further. In reality, what increases is not the rest mass, but the energy and momentum. However, from the perspective of the applied force, the effect is perfectly equivalent. The faster you go, the harder it is to increase even faster. Particle accelerators are a vivid example of this phenomenon. In devices like the Large Hadron Collider, protons are accelerated to velocities extremely close to the speed of light. When energy is added, their velocity barely increases further. Instead, the additional energy goes into increasing momentum and the ability to create new particles upon collision. No experiment has ever recorded a particle with mass exceeding the speed of light. Not because we haven't tried hard enough, but because the equations forbade it from the start. Interestingly, massless particles, like photons, always travel at the speed of light. They cannot slow down, nor can they accelerate. For photons, the speed of light is not an upper limit, it is their only state of existence. This reveals a clear division in the universe. Objects with mass always move slower than light. Massless objects always travel at the speed of light. There are no intermediate states. This limit isn't a preset barrier in space. It's a geometric property of space-time. When you try to push an object of mass to the speed of light, you're not just accelerating through space. You're trying to change how that object exists within the structure of reality, and that structure doesn't allow it. Therefore, the answer to the question why can't we reach the speed of light doesn't lie in a lack of power, but in the fact that the universe simply doesn't have room for that state. Surpassing the speed of light isn't about going faster. It requires a type of existence that space-time cannot support. And to understand this more deeply, we need to look at the universe from a different perspective, one where motion occurs not only in space, but also in time itself. Chapter 6: Space-Time and Cosmic Speed. Everything is always in movement. After understanding that no object with mass can reach the speed of light, a new question arose. How exactly is everything moving in the universe? The answer from the theory of relativity is both simple and fundamentally changes how humans imagine motion. According to Einstein, you don't just move in space. You are always moving in space-time. In common sense, if you stand still in a room, You're not moving at all. But according to the theory of relativity, that's not true. Even if you're completely still relative to the ground, you're still moving, not in space, but in time. This understanding leads to a profound idea. Everything in the universe has a total velocity in space-time. And this velocity is always equal to the speed of light. This doesn't mean you're flying through the room at the speed of light. It means your movement is divided between space and time. If you're not moving in space, all of your movement is in time. If you're moving fast in space, the portion of your movement in time is reduced. This is why time seems to slow down when you move fast. Imagine space-time as a four-way road. You always travel along that road at the same speed. As you turn more toward space, you turn less toward time. There's no way to go faster than the total speed allowed. You can only change direction. This perspective helps explain the strange phenomena predicted by relativity. But it is not contradictory. When an astronaut travels near the speed of light, he is not ruining time. He is simply using more motion for space, leaving less for time. Conversely, when you stand still, you don't waste movement on space. You move maximally in the direction of time. That's why you age faster than someone who is moving very quickly. This also explains why the speed of light is such a unique limitation. Not because there's an invisible wall in space, but because everything has used up the universe's speed budget. Photons use all their motion for space. So there's no longer any motion in time. For photons, time doesn't flow. Objects with mass are different. They always require some degree of motion for the sake of time. Otherwise, they wouldn't exist in the way we understand them. Therefore, they cannot concentrate all their motion into space like light. The speed of light limit, therefore, is not a forbidden law. It is a consequence of space-time geometry. It allows time and space to smoothly exchange roles, but does not allow exceeding the total allowable limit. When you view the universe in this way, you no longer see the speed of light as an arbitrary number. It is a profound constant, connecting motion, time, and existence. And as an object approaches that limit, very real effects begin to appear. Time dilates, length contracts, and familiar concepts begin to bend. Chapter 7: The effects of approaching the speed of light. No longer just theory. When the special theory of relativity was published, many thought its consequences were just mathematical games. Time slowing down, length shrinking, two people aging at different rates. These sounded more like philosophical paradoxes than physical realities. But the universe doesn't care about human intuition. And experiments have proven that. The most well-known effect is time dilation. According to the theory of relativity, a clock that is moving faster will run slower than a clock that is stationary. The important thing is, it's not the clock that's broken, but rather the time itself in the moving system that is slowing down. This phenomenon has been measured firsthand. Extremely precise atomic clocks were placed on airplanes and flown around the Earth. Compared to clocks on the ground, the clocks on the airplanes ran slower. Exactly as predicted by the theory of relativity. The discrepancy was small, but entirely real. A more striking piece of evidence comes from muons. Muons are unstable particles created when cosmic rays collide with Earth's atmosphere. In their resting state, they exist for only an extremely short time, too short to reach the ground from an altitude of tens of kilometers. However, muons have still been detected on the Earth's surface. The reason is that they travel near the speed of light. From their perspective, time slows down, allowing their lifespan to be extended long enough to reach the ground. There are no miracles, no exceptions, only extensions of time. The second effect is length contraction. According to the theory of relativity, a fast-moving object will shorten in the direction of motion, as measured by a stationary person. This is not compression or deformation of the object. It is how space-time rearranges distances. From the perspective of the person in motion, the opposite happens. The distance ahead is shorter. The journey becomes shorter. Not because the speed increases, but because the space is compressed. This leads to one of the most famous examples of relativity theory, the twin paradox. One person remains on Earth, The other boards a spaceship traveling near the speed of light and returns. When they meet again, the traveler is younger. At first glance, this seems contradictory. Why can't we say that the Earth is moving relative to the spacecraft? The key lies in acceleration. The traveler has to accelerate, turn around, change the frame of reference. The person staying behind doesn't. The two journeys in spacetime are asymmetrical. The paradox disappears when the analysis is correct. And the result remains the same. The faster person experiences less time. These effects aren't just true on paper. They have to be taken into account in modern technology. GPS navigation systems, for example, must correct for both velocity-induced and gravitational time dilation. Otherwise, errors will accumulate and cause positioning to deviate by kilometers per day. The theory of relativity is no longer an abstract theory. It is a part of modern life. And all those strange effects stem from a single cause. The speed of light is the absolute limit. As you approach that limit, space and time are forced to change to maintain the order of the universe. But this limitation doesn't just govern movement. It also protects something far deeper: cause and effect. Chapter 8: The speed of light is the speed of cause and effect. Up until now, the speed of light has seemed like a limit to motion. But at a deeper level, it's not a limit to the object itself, but a limit to the effect. In other words, the speed of light is the maximum speed at which a cause can produce an effect. All information in the universe, whether carried by light, radio waves, fundamental particles, or gravity, cannot travel faster than this speed. Not because information is slow, but because the universe does not allow events to connect faster than that. To understand this, physics uses an important concept: the light cone. Imagine each event in spacetime as a point. From that point, light radiates in all directions, forming a cone in the spacetime diagram. Every event within the future light cone can be influenced by the initial event. Every event within the past light cone can be its cause. What about events outside the light cone? They cannot have a causal relationship with the event under consideration. Not because they are too far away, but because there isn't enough time for the light, or any signal, to travel to them. This is how the universe protects its order. If a signal travels faster than light, the light cone will break. In some frames of reference, the signal will arrive before it is sent. This is not only strange, it is a logical catastrophe. An event can become its own cause. The effect can occur before the cause. Cause and effect, the foundation of science and human experience, would lose its meaning. The important thing is, this is not philosophical speculation. This is a direct mathematical consequence of relativity. Simply allowing a signal faster than light instantly allows time travel in some frame of reference. Therefore, the speed of light is not just a number. It is the boundary between what can be influenced and what cannot be influenced. This also helps explain why light plays a special role in all modern physics theories. It doesn't just carry energy. It carries the cause and effect structure of the universe. Each photon is a tiny unit of order. Even gravity, according to general relativity, doesn't travel instantaneously. Fluctuations in gravity propagate as gravitational waves at the speed of light. When a star explodes, not only the light but also the changes in the gravitational field take time to reach you. There are no shortcuts. Interestingly, this limit doesn't make the universe slow. On the contrary, it makes the universe stable. Thanks to it, events are arranged in meaningful sequences. Thanks to it, the past isn't interfered with by the future. Thanks to it, the laws of physics can be applied consistently everywhere. If the speed of light were greater, the universe would still exist, but differently. If there were no limits at all, the universe might not exist in the way we understand it. Therefore, when we say that nothing can move faster than light, we are not talking about an unpleasant barrier. We are talking about a principle that protects the order of reality. However, in modern science, there are still phenomena that seem to break this boundary. They are often referred to as exceptions. But upon closer examination, we will see that they do not violate any rules at all. Chapter 9: These exceptions are not exceptions throughout the history of modern physics. There have been numerous phenomena that have led people to believe the speed of light has been surpassed. From quantum entanglement and the expansion of the universe to controversial experiments involving superluminal signals, all have raised a fascinating question. Is the limit of the universe being broken? The answer, so far, remains no. The most famous phenomenon is quantum entanglement. When two particles are entangled, measuring the state of one particle will instantly determine the state of the other, even if they are kilometers or even light years apart. This once bothered Einstein so much that he called it ghostly interaction from afar. But the crucial point is, no information is transmitted in this process. The observer cannot manipulate the measurement results to send a message. Only by comparing the results through a classical communication channel, which is limited by the speed of light, is the connection realized. Quantum entanglement breaks intuition, but it doesn't break cause and effect. Another example is the expansion of the universe. Galaxies very far away are moving away from us at speeds that seem to exceed the speed of light. But this is not movement through space, but rather the expansion of space itself. Relativity only prohibits objects from moving faster than light in local space, not from space itself expanding. In other words, no galaxy is traveling faster than light, the distance between them simply increases. There have also been experiments that claimed to measure superluminal velocities. Some light pulses in special environments can have group velocities greater than c, even negative. This sounds like a violation of all rules, but upon closer analysis, it is found that the actual information-carrying part of the signal, the front end of the pulse, still does not exceed the speed of light. No message arrives earlier than allowed. What about hypothetical particles like tachyons? Mathematically, they could exist as solutions to an equation. But if they existed in reality, they would break causality. Therefore, to date, there is no experimental evidence for their existence. Interestingly, every time physics approaches the boundary of the speed of light, instead of breaking it, we gain a better understanding of why it cannot be broken. Chapter 10: The Limits of Light, the Foundation of Reality. When science asserted that nothing could surpass the speed of light, humanity once viewed it as a barrier to the dream of conquering the universe. But the deeper we understand, the more we realize that this limit doesn't hold the universe back, it keeps it alive. The speed of light is not just the speed of photons. It is the maximum speed of information, of cause and effect. Thanks to this limit, cause and effect are preserved. Each event can only affect the future, not reverse the past. If this limit did not exist, the concepts of before and after would collapse, and the universe would become an incomprehensible chaos. The limitations of light also force us to abandon the classical notion that space and time are absolute. Instead, they merge into a single structure, space-time. When an object moves quickly, its time slows down, and the space in front of it shrinks. This is not philosophical speculation, but effects that have been measured and applied in modern technology. The amazing thing is, it is precisely because of limitations that order emerges. Stars can exist for billions of years. Atoms are stable. Life has a chance to form and evolve. And intelligence can emerge to question the very universe that gave birth to it. Light not only helps us see the world around us, it defines how the world operates. Every observation, every measurement, every piece of information that humans receive is constrained by this limitation. But it is precisely this constraint that makes knowledge meaningful and reliable. Ultimately, the speed of light reminds us of something profound. Science isn't always about breaking all boundaries. Sometimes, the greatest progress comes from understanding why boundaries exist. And perhaps the most miraculous thing is not that we cannot travel faster than light, but that we can understand it, and find beauty in the order that the universe has chosen. From the dawn of time, humanity has been obsessed with speed. We want to go faster, fly higher, and surpass our own limits. And then, as science advanced, a seemingly simple question began to emerge. Does a maximum speed exist in the universe? Today, we know that light travels at a speed of nearly 300,000 kilometers per second, so fast that in the blink of an eye, It could circle the Earth more than 7 times. But the strange thing is, nothing can surpass it. No spacecraft, no particles, no information can travel faster than light in a vacuum. Why is this the case? Is this merely a temporary technological limitation? Or is it a profound law, woven into the very structure of space and time? If you could surpass the speed of light, what would happen to time, to cause and effect, to the past and the future? In this article, we'll journey from the oldest conceptions of light, through physics-shaking experiments, to Einstein's theory of relativity, to understand why the speed of light is not just the fastest speed, but the foundation of reality.